Welcome back to Physics 191. I'm Gerard Blanchard, and this time we're going to apply our energy equation to more situations. Remember that energy is energy of motion or energy of position, so whenever you have an object changing its speed or changing its position, you should think energy. Our first exercise: a cart moving to the right passes point 1 at the bottom of a hill at a speed of 20 meters per second. And the question is, what is the speed of the cart as it passes point 3, which is 10 meters up the hill? And neglect friction. So since the cart is rolling, we will consider the effect of friction on the cart to be negligible or too small to matter. So we have a change in position, a change in speed. You should think energy. So draw your diagram, get all the information you can out of this statement, think energy, and see if you can get the answer before I give it to you. Okay, here's our hill, and we initially had the cart. We'll call its initial height 0. We're given V initial to be 20 meters per second, and point 3 was somewhere over here. And that's the end as far as we're concerned, or at least for this time period, that's the end. And so the height is equal to 10 meters. Height final is 10 meters. And V final is equal to, that's what we're looking for. What is the speed of the cart? So the cart has moved 10 meters up the hill. It's changed its speed. We're asked for the change in speed. Change in position, change in speed should make us think energy. And we have the work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. Or the work done by non-conservative forces is the final kinetic energy minus the initial kinetic energy plus the final potential energy minus the initial potential energy. Let's think about what is 0 here. We have an initial height of 0, so the initial potential energy will be 0. And that's it. Kinetic energy initial is not 0, and its final height is not 0. So we can't do anything more with that. And so we have work done by non-conservative forces is equal to 1/2 mv final squared minus 1/2 mv initial squared plus mg height final. Now let's think about this work done by non-conservative forces. Let me draw the cart again. I'll draw it over here. Okay, and the forces acting on it are weight, normal force, and so the cart's moving like this. Weight is conservative. That's the gravitational force. So weight is always conservative, so we never have to worry about that in terms of non-conservative work. So weight is conservative. The normal force is not conservative, but just as in our last example, last time with Jim on his skateboard on a quarter pipe. The normal force is always perpendicular to the surface, and the motion is always parallel to the surface. So the normal force is always perpendicular to the motion, so the angle between the normal force and the motion is always 90 degrees. So the normal force doesn't do any work here either. So if we neglect friction, there are no non-conservative forces that do any work. So the work done by non-conservative forces in this case is 0. So work non-conservative is also 0. So we have 0 equals 1/2 mv final squared minus 1/2 mv initial squared plus mg height final. V final squared is what we're looking for. We know V initial, we know G, and we know height final. The only thing we don't know in this equation is the mass, but that's okay, because all of the terms have mass in them, and we can divide both sides by mass. 0 divided by mass is 0. 1/2 mv final squared divided by mass is just 1/2 v final squared. Divide out the mass here, 1/2 v initial squared plus g times height final, and we have all of the information we need to answer our question. So let's start putting in some numbers. 0 is equal to 1/2 v final squared minus 1/2 of v initial squared, which is 20 squared, plus 9.80 for g times height final of 10. And I have 0 is equal to 1/2 v final squared minus, let's see, 1/2 of 20 squared. Well, 20 squared is going to be 400, and 1/2 of that is going to be 200, so minus 200, and 9.80 times 10 is 98, so plus 98, and so 0 is 1/2 v final squared minus 200 plus 98 would be minus 102. Now I will add 102 to both sides. I have 102 is equal to 1/2 v final squared. I'll multiply both sides by 2. 204 is equal to v final squared. So the square root of 204 is equal to v final. And so finally, we have the square root of 204 is 14.3, and since that's a velocity, it would be meters per second, is equal to v final. So when the cart reaches its position 10 meters high on the hill, its speed will be 14.3 meters per second. Now let's go back to that question. And let's ask another question. Will the cart reach position 4, where position 4 is 20 meters high? Well, let's just ask ourselves, what is the speed of the cart when it reaches position 4? So what I'd like you to do is repeat what we've just done, but with a final height of 20 meters, and see what the speed is there. So try that, please. Okay, let's start from 0 height and wind up at 20 meters height. So height initial is equal to 0. V initial is equal to 20 meters per second. Height final is equal to 20 meters. V final is what we're looking for, and the cart goes all around up here. And the forces on the cart are work, which is conservative, normal force, which is perpendicular to the surface, and we have a change in position, a change in height, makes us think energy. Our work non-conservative is equal to, and I'll just go ahead and write out kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And we decided that there was no non-conservative work being done because weight is conservative, the normal force is perpendicular to the ramp, and we're neglecting friction. So work non-conservative is 0. The initial potential energy is 0 because we started off from 0 height. And now we'll continue on. 0 is equal to 1/2 mv final squared minus 1/2 mv initial squared plus mg height final. And this time what I will do is I will add 1/2 mv initial squared to both sides and subtract mg height final because we know that we're looking for v final. So I'll write that as 1/2 mv initial squared minus mg height final is equal to 1/2 mv final squared. I'll divide through by m. It turns out that the mass of the cart doesn't matter at all. Any mass would give us the same answer. And I'll multiply through by 2. Multiply everything by 2 to get rid of this 1/2 right here. So I have v initial squared minus g height final times 2 is equal to v final squared. And we can start putting in our values. V initial is 20 squared minus g 9.80 times height final, which is 20 times 2 is equal to v final squared. And let's see what we have here. We have 20 squared minus 9.80 times 20 times 2, and we have 8 equals v final squared, or v final is equal to the square root of 8. The square root of 8 is 2.82 meters per second is equal to v final. So when the cart reaches a height of 20 meters, it is moving at 2.82 meters per second. So does it reach height? Does it reach 0.4? Yes, barely. It only has a little bit of kinetic energy left, but in fact, it did manage to reach a height of 20 meters. So the cart traded in its initial kinetic energy for potential energy. When it had enough potential energy to get to, it had enough kinetic energy to get the potential energy that it needed to get 20 meters high, and still had a little bit of kinetic energy left. So the cart could have gotten even a little bit higher. And if you want to, I'm not going to work this out, but you could calculate the height that the cart could ultimately reach. Okay, let's do another exercise. Here we have two crates, one of which is on a ramp and one of which is hanging. And the question is, a crate of mass M1 on a frictionless inclined plane is attached to another crate of mass M2 by a massless rope. The rope passes over an ideal pulley so that the mass M2 is suspended in the air. The plane is inclined at an angle theta equals 36.9 degrees. Use conservation of energy to find out how fast crate M is moving after M1 has traveled a distance of 1.4 meters along the incline starting from rest. The mass of M1 is 1.24 kilograms and the mass of M2 is 16.3 kilograms. Okay, that's a lot of information, but we approach this just like we do any other question. We'll draw our diagram, we'll list all of our knowns and unknowns. We're already told to consider energy, and we can answer this question. There's a couple things you need to know, one of which is that you have to consider the kinetic energy of both crates and the potential energy of both crates, but you can do that separately. You can calculate mg height initial and final separately for each crate. And since the two crates are tied together, they will have the same speed. So go ahead and get started on drawing your diagram, listing all of your knowns and unknowns, and then considering energy to answer the question of how fast the crates, both crates, are moving after the crate on the ramp has traveled a distance of 1.4 meters along the ramp. So go ahead and get started. Okay, let's draw our diagram. The angle of the ramp is 36.9 degrees. We have M1 and M2, and we're going to call them both at the same height initially. We'll call it height 1. Height 1 initial is 0. Height 2 initial is also 0. And they start from rest, I believe. Yes, they start from rest. So V1 initial is equal to 0. V2 initial is equal to 0. So we just have to be careful about getting all of our information from the statement. Have them tied by a rope. And the mass 1 is 12 0.4 kilograms. Mass 2 is 16.3 kilograms. And let's see, crate of mass M1. The rope passes over an ideal pulley. The plane is angled at 36.9 degrees. Crate M1 has traveled a distance of 1.4 meters along the ramp. So the crate moves up the ramp. Okay, a distance of 1.4 meters. Distance is 1.4 meters. Now that means that this crate has gone down 1.4 meters. So that would say height final is minus 1.4 meters. V2 final is just V final, whatever that is. V1 final is the same thing, V final, whatever that is. And we have not figured out height 1 final. Height 1 final, we have to figure out. Well, actually we can figure that out using trigonometry. We know that the distance that the crate moves up the ramp is 1.4 meters. We know that this angle is 36.9 degrees. So height final, the amount by which the crate has increased in height, is equal to this side of the triangle. If this is 1.4 on this side, this is 36.9 degrees right here, then this is the opposite side. So height 1 final would be equal to 1.4 times the sine of 36.9 degrees. 1.4 sine, 1.4 meters, sine of 36.9 degrees, which is 1.4 times the sine of 36.9 degrees, 0.84 meters. 0.84 meters. And whew, we've finally gotten all the information from that statement. It was a complicated question, but straightforward to analyze. We just took it one step at a time and got all the information we could, one piece at a time out of it. So we have now completely analyzed the question statement. We have to bring in our physics, and we have to recognize that we have a change in position and a change in speed, so that this is an energy situation. And for an energy situation, we write down the work done by non-conservative forces is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Now let's think. Are there any of these that we can zero out? Yes. Initially, both crates are not moving, so the initial kinetic energy is 0. So the initial kinetic energy is 0. Also, we called the height of both crates to be 0 initially, so the initial potential energy is also 0. Okay, so we've already reduced 2 of our terms. Now let's think about work. Let's consider the forces on each of those crates. Well, let's take this crate right here. The forces on it are weight and the tension in the rope. Okay, so the work done, well, weight, remember, is conservative, so we don't have to worry about that. The work done by the tension would be tension times the distance that the crate moves, 1.4 meters, times the cosine of the angle between the tension force and the motion, which is down. So the tension and the motion are 180 degrees apart. So tension times 1.4 times cosine of 180 degrees is the work done on crate 2. How about crate 1? Well, on crate 1 we have weight, we have normal force, we have tension, no friction. We were told that this is a frictionless inclined plane, so we have no friction to worry about. And so weight is conservative, so not one that we have to worry about for the work. The normal force, always perpendicular to the motion, so normal force is not going to do any work on the crate. The only thing that we have is tension, and so we have a work of tension times the distance that the crate moves, tension times 1.4 meters, times the cosine of the angle between tension and the motion. And the tension and the motion in this case are in the same direction, cosine of 0 degrees. And that's all of the non-conservative work to consider. And that's equal to kinetic energy final plus potential energy final. Well, let's think about this. Tension is the same. It's the same rope, so same tension acting on both boxes, so this tension is the same. These distances are the same as well. So I can factor them out. I can have tension times 1.4 times cosine of 180 degrees, which is minus 1, plus cosine of 0 degrees, which is 1, and minus 1 plus 1 is 0. So this whole term goes to 0. So in fact, the non-conservative work done on the boxes is 0, and that's because, in fact, tension is an internal force in this case. Whatever work it does on one crate, it does an equal and opposite work on the other crate. If we consider the two crates as a single system, then there is no non-conservative work done on the crates by the tension. It cancels itself out because it's an internal force. Okay, so 0 is equal to kinetic energy final plus potential energy final, or I will subtract potential energy final from both sides. So minus U final equals kinetic energy final. Okay, so minus U final would be minus mass 1 G height 1 final plus mass 2 times G times height 2, should be height 1, height 2 final is equal to kinetic energy final. So that would be 1/2 mass 1 V final squared plus 1/2 mass 2 V final squared. Okay. Let's see. In this case, we have the same G, so I will factor that out. So I have minus G times M1 height 1 final plus M2 height 2 final. And here I have 1/2 V final squared. So I'll factor out the 1/2. And then I have m1 plus m2 v final squared. So I have 1/2 m1 v final squared and 1/2 m2 v final squared. So now we can start putting in our values. We have minus 9.8 O for G. Mass 1 is 12.4. Height 1 final is 0.84 plus mass 2. Mass 2 is 16.3. Height 2 final is minus 1.4 equals 1/2 mass 1, 12.4 plus mass 2, 16.3 v final squared. And let's do some calculations. We have minus 9.80 times the quantity 12.4 times 0.84 plus 16.3 times negative 1.4. Let me review all of that to make sure I've put it into my calculator correctly. Minus 9.8 times the quantity 12.4 times 0.84 plus 16.3 times negative 1.4. That gives us a result on this side of 100, we'll call it 122. So 122 equals 1/2 times the quantity 12.4 plus 16.3, and that is 14.4 v final squared. Okay, we're almost there. All we have to do is divide both sides by 14.4 and take the square root. So 122 divided by 14.4, take the square root, that will be, excuse me, that will be v final. Square root of 122 divided by 14.4 equals 2.91 equals v final, and v final speed will be meters per second. So after the crates have moved 1.4 meters, they are both moving at 2.91 meters per second. And this, as complicated as it was to do those calculations, it's a lot simpler than it would have been if we had to consider acceleration, time, forces, and so on. So we could have answered this same question using Newton's laws, but that would have been even more complicated. As much calculation as we had to do here, it turned out to be a lot simpler to use energy because a lot of the things in our energy equation were zero, and it was just a straightforward conversion of potential energy into kinetic energy. Okay, let's work one more example. George bungee jumps from a bridge that is 55 meters over the river below. The bungee cord has an unstretched length of 27 meters. The bungee cord stops George's fall when he is 2 meters above the river. If George has a mass of 75 kilograms, what is the spring constant of the bungee cord? So we have to save George's life. We don't want George to hit the river, so we have to calculate the strength of the bungee cord that we use. In practice, what would happen is you would use a thicker or thinner bundle of bungee cords to have just the right spring constant to keep your bungee jumper from hitting whatever it is at the bottom of the jump. And this is the kind of calculation that you have to do. Now, one thing to remember is that the bungee cord is initially unstretched. When George is standing up on the bridge, the bungee cord is not stretched, so the initial elastic potential energy of the bungee cord will be 0, but when it is stretched, the bungee cord will have elastic potential energy. So we will be transferring some of George's potential energy into elastic potential energy. So think about that. Draw a diagram. List all your knowns and unknowns. We have a change in position and a change in speed. So this is an energy situation. Think about it and see if you can save George. Okay, let's draw our situation. Here's our bridge, and here's the water. And we have George up here on the bridge. His height initial is 55 meters. If we call the water height 0, so we'll call the water height 0. When George bungee jumps, he will end up 2 meters above the river. Yes. So height final is equal to 2 meters. So George starts off at a height of 55 meters, ends up at a height of 2 meters. George's initial speed, V initial, is 0. And when he comes to rest just above the river, his final speed is also 0. So V final is also 0. Let's think about the bungee cord. The length of the bungee cord, the unstretched length of the bungee cord, we'll call that L0, is 27 meters. And initially, the bungee cord is unstretched, so L initial is also 27 meters. So the bungee cord is unstretched to begin with, so it has a length of 27 meters. What is the final length of the bungee cord? Well, if the bungee cord stretches all the way from the bridge to 2 meters above the river, then the final length of the bungee cord must be 53 meters. So 53 meters from the bridge to the water, and then another 2 meters to the water. So the final length of the bungee cord is 53 meters. And the final thing that we're told is that George has a mass of 75 kilograms. So mass is equal to 75 kilograms. We have a change in position and a change in speed. So this is an energy situation. And we start off our energy situations with work, non-conservative, is equal to K final minus K initial plus U final minus U initial. And what can we zero out here? Well, actually, we can zero out the initial kinetic energy because George is not moving to begin with. We can also zero out the final kinetic energy because he's not moving at the end. So those are both zero. Work done by non-conservative forces. Let's think about the forces on George. Well, the forces on George are the weight and the elastic force, or as Fe, the elastic force from the bungee cord. Well, weight is a conservative force, as it's always been. We have a potential energy associated with weight. We also have a potential energy associated with the force of the bungee cord, our elastic potential energy. So both of these forces are conservative forces. If we neglect friction, such as air resistance, then there are no non-conservative forces acting on George, so the work done by non-conservative forces is zero. So we have zero is equal to potential energy final minus potential energy initial, or potential energy initial equals potential energy final. Okay, now we have to think about the types of potential energy that we have. We have gravitational potential energy, so we have UG initial, and we have elastic potential energy, U elastic initial, and that's equal to gravitational potential energy final plus elastic potential energy final. So this is the first time that we've had to consider elastic potential energy, but since we're dealing with a bungee cord, which is an elastic object, we do have to consider that. So we have gravitational potential energy, mg height initial, plus the elastic potential energy. If you remember, elastic potential energy is 1/2 mass, it's 1/2 K, 1/2 of the spring constant, times the length, the initial length of the spring, the bungee cord, minus the zero length of the bungee cord, squared, and that's equal to mg height final plus 1/2 K times the final length of the bungee cord minus the unstretched length squared. Okay. We have another term that we can recognize to be zero. The bungee cord is initially not stretched, so its initial length is equal to its unstretched length. So L initial minus L0 is 0, which makes this whole term 0. And now we know everything else. We have, what I'm going to do is I'm going to subtract mg height final from both sides because I know that we're looking for the spring constant. So I will have mg height initial minus mg height final is equal to 1/2 K times the final length minus the unstretched length of the bungee cord squared. And I'll multiply both sides by 2 to get rid of that 1/2. And I'll divide both sides by length final minus length 0 squared. So that will give me 2 mg height initial minus mg height final is equal to k divided by length final minus length 0 squared. So 2 mg height initial plus mg height final divided by length final minus length 0 squared equals k, and that's what we're looking for. So let's put in our numbers. Twice mass of 75 times 9.80 times height initial of 55 meters minus 75 times 9.80 times height final of 2, all divided by length final minus length 0. Length final was 53 meters minus 27 meters squared is equal to our spring constant. So we'll do some calculations. And I'm going to factor out, when I do my calculations, I'm going to factor out the 75 and the 9.80 to make my calculations easier. So 2 times 75 times 9.80 times 55 minus 2. Divided by 53 minus 27 squared gives me a spring constant of 115 and that would be, in basic metric units, it would be 115 newtons of force per meter of stretch. And that is the strength of the bungee cord that we need to keep George safe. Now, once again, this would be a fairly complicated problem to solve using Newton's laws. You actually would need calculus to solve this using Newton's laws. So once again, using energy considerations allows us to answer questions that we might not be able to answer otherwise. Next time, we will continue to consider energy. So until then, think energy and think physics.